Hello everybody, welcome to my presentation about aviation power plants. My name is Matthew Dillon. So on the list of discussion today is history of the internal combustion engine. How do internal combustion engines work? Today's internal combustion engine, the history of the jet engine, how does a jet engine work? Today's jet engine, electric propulsion then and now, as well as some of my predictions about some of the future of aviation power plants. So the history of the internal combustion engine actually dates back to the early 1500s, starting out with Leonardo da Vinci. You can go and look up some of his work. They were just like some really crude stuff. And then as time went on, during the late 1700s, early 1800s, we started seeing more steam engines and whatnot. But in the late 1800s, about 1862, the Nicholas Otto designed the four-stroke engine, which is actually technically known as the Otto cycle engine. So the engine itself actually has 4 strokes, or 4 cycles that it goes through. You have the intake cycle, which the intake valve opens up from the cam movement and it draws in the fuel and air mixture. And then as the crank goes around, the piston goes down to the bottom dead center, and then it goes around and comes back up over here. As the piston comes up nearing top dead center, it compresses that fuel and air mixture, and here both of the valves are actually closed. Next is the power cycle. So basically, once this gets up here to top dead center, everything is in line. The rod, the piston rod, and the crank are all straight up and down. And here you have the power stroke. So the spark plug fires off the fuel air mixture under high compression, and it fires it off, driving the piston back down, and the crank moves around. And then as the cycle gets ready to start all over again, on the way back up, the piston is actually pushing out the exhaust through the opened exhaust valve here. So some of the parts are, that you got the crankshaft, and actually the center point is in between these two, about like right here. And then you have the piston rod, or the con rod, or just the rod. And then you have the piston. And then you have valves and some sort of cam. And the cam is what, it's the valve opening timing, basically, is what camshafts are doing. Here we have a couple of different types of internal combustion engines, or more like different ways of induction and exhausting. So this is an overhead cam engine, where the camshaft actually sits overhead of the piston cylinders and whatnot, and the piston itself, I should say. And you have oblongs. So here's a better picture of a camshaft. It's a shaft and it has oblong lobes, or what they're called. And as the crankshaft spins this belt here in this situation, spinning this gear, and the shaft turns, opening, or the lobe goes around and pushes down on the valve, opening up the valve, letting in the intake mixture, and then the same thing on the exhaust side. Over here, what we have is what they call a push rod style of engine. So you have push rods instead of the cam opening with valves right on top of it. So the cam is still a similar design. It pushes on this rod here up to the rocker arm. You can also think of this as like a teeter-totter. It pushes down on the valve, and then there's a valve spring in here that's kind of capturing the valve. So it pushes against the tension of the spring, pushing the valve down. Same thing over here. It lets in the intake or lets out the exhaust, either whatever one works at that time. And then when the lobe completes its down here, when the camshaft lobe completes its revolution, then the spring tension takes back over, closing the valve itself. So, as alluded to way back in the beginning of our class here, that we already talked about the Wright brothers and whatnot. So here's the engine that they actually used, and the really interesting things about this engine are it didn't have spark plugs, it didn't have a carburetor, so that means it didn't have a throttle, and it didn't have a fuel pump or a water pump. So you have compression.
We're sorry, the number you have dialed is not in service at this time.
So inside that cylinder on the other engine, on the engines here, you have the compression, and that can actually, without a spark plug, also be able to ignite on its own because of high compression. It compresses it so much it ignites. So back on this engine, it didn't need spark plugs because on the engines here, you have the compression, and that can actually, without a spark plug, also be able to ignite on its own because of high compression. It compresses it so much it ignites. So back on this engine, it didn't need spark plugs because of the high compression that it had for what it is. The engine only made 12 horsepower, which is really interesting because I have my little fuel saver car is about 110 horsepower, a little Saturn, give about 40 miles to the gallon. This engine makes only about 12 horsepower, but it was good enough, and the Wrights, to their calculations, believe they only needed 8 horsepower. So I guess they exceeded the numbers that they needed. As far as the cooling goes, there's no cooling fins on the cylinders or the crankcase or anything, so they used water injection. So think of it as opening up a faucet. You can adjust the amount of flow by that handle on your faucet. So they did this, and there's actually, the way that the engine is molded, there's water jackets inside for the water to flow around but not actually get inside the cylinders to help cool it off. But instead of circulating the water, there was a hole on the other side of the engine, so as the water went in, it evaporated. Evaporation can also cause a little bit of cooling, but not that much. It's a really inefficient way to cool an engine, obviously. And then it obviously didn't need a fuel pump because it just used gravity feed. And then there is a YouTube video on this. You guys can go and check it out. It's an annual running of the Wright brothers engine. It's about a 5-minute video if you're looking for it. And the engine startup is actually at the time of 3 minutes and 55 seconds. Modern internal combustion engines. So we're starting to see more fuel injection versus carburetor, and we're starting to see electronic ignitions instead of old magnetos. So here's a magneto. It's usually mounted on the back of the engine or somewhere wherever it can get mechanical assistance from the engine itself. So as the engine turns, it turns away at this magneto, which has some gearing inside of it and a plate that goes around and completes the circuit for each spark plug, allowing the spark plug to fire off. With these newer engines, you can actually have a coil pack for each spark plug, and on this engine, and on all aviation engines for piston powered stuff, they're going to have redundancy, so it's going to have 2 spark plugs per cylinder in case you have a spark plug fail or you have a magneto fail. So you would actually have 2 of these. And on the newer engines, some of them are starting to come out to where you would have 12 of these guys to control the spark. Now, fuel injection versus carburetor. So here's a carburetor. You have the fuel inlet. The fuel comes down here and it kind of puddles up. And then the airflow of the carburetor, as the air flows through the carburetor into the engine, it's also bypassing some of this air going down here, and it kind of pressurizes the fuel here, and the pressure puts pressure on the actual liquid fuel, and it sprays out. The fuel injection over here, this is an older style of fuel injection, but it kind of helps you get the idea. So you have basically just think of your fuel tank, you have your pumps, and then it feeds through the throttle body here. And this, all by the throttle opening and closing, it allows fuel to bypass through that, go up here to this, like a separator or a spider injection unit kind of a thing, and it allows fuel to flow through each of these fuel tubes into the cylinders. Newer engines will have separate fuel injectors per each cylinder. So moving on to the jet engine. So the actual first patent that was ever written was by the Frank Whittle in 1930. He was an English engineer and scientist. He was actually one of the original designers of the jet engine. But the first engine to actually take flight was actually in 1939 on the Heinkel HE-178. The reason that Frank Whittle never actually was able to go through with it is because at that time the jet engine was all theory and it really wasn't much of anything, at least not what the English government thought of it anyway. Like the internal combustion engine, you have intake, compression, combustion, and exhaust. An easy way to remember those cycles are suck, squeeze, bang, and blow. So right here, you have the air coming in and it's being compressed. So you'll notice that the size of these impellers here change, and you'll see it on a couple other pictures later on. As it changes, the compression of that air gets more and more, and then the fuel down here, through some different bypass valving and stuff like that, and ducting, the fuel gets injected and then it gets lit, and as that fires off, it goes down different piping in different tubular areas. So just think of it as a water hose with your finger over it. You got it trickling out, and then you put your finger over it, it comes out at a higher rate of speed. And that pushes the impeller shafts, which you kind of see there at the end of the engine. It spins those, and it's all connected to the same crankshaft from the front of the engine to the rear. So you have different styles of turbine engines, and the styles that you see here are turbojets, which were a lot of the older style military aircraft. Then they started going to the turbofan, the low bypass stuff. So it's not as big around, but you still have a fan in the front of the engine, kind of like this. And then you went to the high bypass turbofans, which is like this guy. So the bypasses mean how big the fan is in compared to the engine. So this is the engine right here. And then you have bypassing, so it creates thrust here, but it's also creating thrust here. It's just obviously not as much out here, but it helps, about 30% in some cases, not all. And the first successful jet aircraft to fly was the ME-262. And modern jet engines, much like the internal combustion engine, really haven't changed much over the years. Materials, fuel systems, of airflow throughout the engine. The tighter you can make an engine, the more fuel and air it can actually utilize all the way, thus making more power. So that's why you would have that. Electric power. So you're starting to see the advent of electric power on some of the aircraft that we're seeing today. Basically, the electric motor, on this case, and pretty much all DC three-phase motors, is you have these are all magnets out here. And if you remember back to grade school, elementary school, you'd remember that north and south poles on magnets attract to each other, but north and south oppose each other, or repel each other. So basically, these are electromagnets in here, and these are just standard already magnetized magnets. So basically, when you add power to this, it turns it into a magnet. So what it'll do is all these will be kind of the same polarity. So let's say these are all north, these will all be north, and then whenever it adds power to this one, it'll become a south. So then as the next magnet tries to come near it, it'll all of a sudden switch to the other side of the motor. So it kind of attracts it all the way around. So it's like basically going from one magnet to the other, changing as it goes. But of course, this changing from here to here is, it's split seconds, basically, thousandths of a second. So the first electric powered aircraft actually flew back in 1883. It was basically a dirigible, so it was a rigid airship. And it utilized hydrogen to make it float, and it had a 1.5 horsepower electric motor on it. Electric motors have, much like the internal combustion engine and the jet engine, really haven't come that far. It's just the way that they are is by materials and tolerances and different things to make them more efficient. Electric motors have gotten better as far as windings and stators and stuff like that, but the major change is the batteries. More powerful and lighter batteries. So where will aviation power plants go from here? Well, internal combustion engines, I'm hoping we're going to see more fuel fuel efficient, so fuel injected electronic ignition. Hopefully that'll start coming down in price as it becomes more popular. We're going to start seeing different fuels as 100 low lead is starting to become quite a commodity in some areas, and it's not as bad here in the United States yet, but it's getting that way. I think we're going to start seeing more electric powered aircraft and maybe even some hybrid options. As far as jet engines, I'm thinking it's probably going to be more fuel efficiency, quieter, and less emissions. With like the GE Gen X engines, they're about 15% more efficient, 15% quieter, which is a big deal overall in money savings. As far as that goes, the materials are also going to be what's going to make an engine different, especially on jet engines. Carbon fiber on those inlet fans and whatnot, and titanium has already been used for many years on the inlet guide vanes and impeller blades. Here are my resources for the photos. My resources used for the investigation of going back into time and doing the research for y'all. And that's it. So if anybody has any questions or comments, just please leave them in the discussion down below, and I'll answer them. I'll make sure I keep on top of it and answer throughout the next couple weeks in case there's some stragglers wanting to ask some questions. But we'll just talk to you guys later. See ya.